And first thing I wanted to do was just sort of review a little bit of what we did last Thursday. I didn't get the material posted till this morning because I forgot. Um, we ended up driving over to Seattle right after class, and I'd had the stuff processed on YouTube, but then forgot to post it. So, but it's up there now. The other day we started looking at capacitors, and we found out that for a parallel plate capacitor with air between the plates, the capacitance ends up being epsilon naught A over the separation between the plates. And found out that you have to have just about an enormous area in order to have a capacitance of 1 farad. And actually, they're really air-spaced capacitors aren't practical. So they're almost always is a dielectric between the plates. But we're not going to end up studying that too much. What I'd like to do is learn a bit about energy stored in capacitors. Oh, and also I was just going to start with introducing a couple of ideas. They derive the expressions for these in section 14.1. This is for a parallel plate capacitor. They also derive the expression for a cylindrical capacitor. And for a cylindrical capacitor, it's usually written as the expression is usually capacitance per unit length. And that ends up being 2 pi epsilon naught divided by the natural log of the radii of the charge-bearing surfaces. And you could kind of imagine that you have an inner cylinder in a cylindrical capacitor and then an outer cylinder, and you'd have charge of one type on the outer surface, maybe positive and negative on the interior, or vice versa. Doesn't matter. But the smaller one is R sub A, and the larger radius is R sub B. And I don't know that we'll do much with that, although there is one homework problem that I've used for that. But anyway, this is a cylindrical capacitor, which, who knows, there might be a use for such a thing sometime. And then there's also a spherical capacitor, which is going to be tricky because somehow you have to poke a hole in the outer one to get a wire into the inner one, unless you can somehow go into 4-dimensional space and just kind of warp it around. But anyway, it ends up being 4 pi epsilon naught times RA over RB over RB minus RA. And again, RB, well, don't worry about that one. I don't think we're going to actually do anything with that. But for starters, wanted you to consider a parallel plate capacitor and look at a kind of conceptual problem. And I don't remember if I may have gotten this out of a book that was written by one of my physics professors at Eastern, and it was just filled with conceptual problems about all sorts of different things in physics. And it was kind of a nice book, actually. I used to use it. My students dreaded what we called the Gibbs problems. It was written by a guy named Robert Gibbs. And but anyway, let's take a look at this. We have a circuit that consists of a battery, a 3-volt battery, and we just drew it looking cylindrical there, and an ideal 1 picofarad parallel plate capacitor connected with good copper wires. Okay, so these represent good copper wires here. And assume the battery has been connected for some time. Now, what that tells us, if it's been connected for some time, is that The capacitor will be fully charged, so it's going to have positive charge on the upper plate, and it'll have negative charge on the bottom plate. Fully charged, and there's no current flowing in the circuit anymore. Okay, so first question is, what is delta V12? Well, that's from this point to this point, and we're in an electrostatic situation, and in that situation, there is no electric field in the conductors. And so there's no electric field in here, and since delta V is equal to the negative of the integral of E dot dl, if E is zero, delta V is zero, there's no potential difference between 1 and 2. And this is typical that in a circuit like this, there's no voltage drop within the wires if they're good wires. Even if you do have an electric field in here, you just have a continual charge flow and you don't see voltage drops in the wires themselves. Similarly for delta V23, that's from here to here. There's no potential difference there. Now, delta V34, that would be the potential difference across the capacitor. Well, since there's no potential difference from here to here, and there would similarly be no potential difference from here all the way over to the bottom of the battery, the potential difference between 3 and 4 is going to be the same as the potential difference across the battery, which is 3 volts. So 3 volts. And this equals 0, this equals 0. So it's just something that happens in there. Then the value of the electric field at 0.5. Well, since there is a 3 volt potential difference here, and it's 1 millimeter between those two things, in a parallel plate capacitor, we make the assumption that the electric field is uniform in there. So we've got a uniform electric field, and when you have a uniform electric field, the absolute value of the potential difference is just E times D. This electric field strength times D, or the electric field is just going to equal the absolute value of the potential difference divided by the distance, which in this case is going to be 3 volts divided by 1 times 10 to the minus 3 meters. And remember, a volt per meter is a legitimate unit for electric field. So we'd have 3,000 volts per meter. Sounds like a lot, but it's only a 3 volt potential difference across this little 1 millimeter gap here. Then it says, insulating handles are used to pull the plates apart slightly while the battery remains attached. Then you wait for a while, and in actuality, a brief instant is long enough to pick up your pencil. And then for each of the following quantities, state whether they increase, decrease, or stay the same. Well, delta V34, we still have the battery connected in the circuit. If you wait for a brief instant, the electric field will drop to 0 within the wires, and so delta V34 is going to be the same as that of the battery. It'll still be 3 volts. So this is only asking for each of the following quantities, state whether they increase, decrease, or stay the same, and delta V34 is equal to the same. Now, what about the charge on the plates? Well, think about a capacitor here. The capacitance is the charge over delta V, and in this case, epsilon naught A over D. Delta V doesn't change, but the D does. It's going to increase, which means the capacitance will decrease, which means the ratio of charge over delta V is going to decrease. But if delta V doesn't change, if it stays the same, and this has to decrease, the capacitance decreases, then Q must decrease. Okay. Now, sigma refers, you probably can't read that worth beans, but it would refer to the surface charge density on the plates of the capacitor. Well, we didn't change the area of these plates, so if the charge decreased, the surface charge density must decrease. So that has to decrease. The electric field at 5, well, we still have the same potential difference, but we have a larger distance. Okay, doesn't say how much we increase the separation by, but we'd be dividing by a larger distance. Maybe you've doubled it to 2 millimeters or something like that, but the electric field strength is potential difference over distance. And if distance increases, then the electric field decreases. And then we already answered this, the capacitance will decrease as well. So this is looking at a capacitor in a circuit. Okay. One other thing I wanted to consider here was last Thursday we looked at capacitors in series, and no, we looked at capacitors in parallel. And for capacitors in parallel, and I'll just write this caps in parallel, we end up with the equivalent capacitance ends up equaling C1 plus C2 plus ... however many you happen to have in parallel. So capacitors in parallel add like resistors in series. Let's take a look at capacitors in series. I think I've got a dying pen here. Time to grab a new one. This one's not acting so great either, but that's okay. I'll live with it. Let's just imagine that we have a circuit set up here, and it's got a battery in here that has a potential difference, delta V across it. And then just for the heck of it, we'll put 3 capacitors in series in this circuit. And I didn't draw it in the circuit, but I'll put a little switch down here, and just imagine that at time 0, I happen to flip the switch down here and let charge flow around in the circuit as much as it wants to, but I'll have a C1 here, a C2 here, and a C3 here. And once I've got that circuit thrown, the potential difference across all 3 of these capacitors will add up to delta V. So I'll have a delta V1 here that I could put a voltmeter on, a delta V2, put a voltmeter on that one, delta V3, put a voltmeter on that. And I'd find out that delta V1 plus delta V2 plus delta V3 is equal to delta V. So that's something that'll be true. Now, what's going on in here? Well, each of these capacitors has the ability to store charge in the presence of a potential difference. And in fact, the capacitance is equal to the ratio of how much charge is on it divided by the potential difference across it. So there's something I can write, and I can write that for each one of these capacitors. C2 is equal to Q2 over delta V2. C3 is equal to, whoops, that's supposed to be Q2, Q3 over delta V3. So those are things that I can say. And doesn't matter how much charge you put on a particular capacitor, the capacitance is such that that ratio of charge over delta V will stay constant. All right, well, now often we imagine, even though we know it's the negative electrons that are what move around in a circuit, we imagine that there's positive charge that goes in this direction. Now, it's actually negative charge going in the opposite direction, but for nearly everything we do, we can consider it to be positive charge going this way. And so let's imagine after we've thrown the switch, we'll get a positive charge build up on here, and that'll be, there will also be negative charge of an opposite amount on that thing. So this will be Q1. This will be minus Q1 down here. There will be positive charge on top of C2, which will be Q2. And I know I'm writing that way too small, but here's the thing. This entire part of the circuit has no electrical connection. If I go draw a line through the middle of capacitor 1 and through the middle of capacitor 3 and then connect those things, all of that stuff is divorced from the battery. There's an air gap between those things, and you don't get current flow across an air gap unless you're experimenting with the photoelectric effect, which we're not. So turns out that the charge that's up here on Q1 is the same as the charge that's on the bottom of C3 down here, which would be minus C3. But it turns out that the charge stored on each of the capacitors, any charge that shows up on top of C2 had to come off of the bottom of C1, which was initially neutral. And so you end up with Q1 equals Q2 equals Q3. And they may discuss that in the book a little more clearly than what I just did, but that's something that we'll have anyway. So let's just call it Q. Okay. Now, I'm going to solve each of these equations for delta V. And what I'll get is delta V1 is going to equal, it's actually Q over C1. Delta V2 equals Q over C2, and delta V3 is equal to Q over C3. And in each case, I've replaced what had been Q1s and Q2s and Q3s with just plain Q, because it's the same on every one of them. And now I can use this thing. My delta V is going to equal the sum of these three things. And what I'll get if I add these three things together is going to be Q times, I'm doing a couple steps of algebra here, 1 over C1 plus 1 over C2 plus 1 over C3. And that's what that happens to be. But if I play around with, well, just our regular capacitance formula, where C is equal to Q over V, that means V is equal to Q over C. And let's see, or actually 1 over C will equal V over Q. That's handier right now. Okay, well, if I take delta V and divide by Q, delta V over Q, that'll be my equivalent, or it'll be 1 over my equivalent capacitance, and it ends up equaling 1 over C1 plus 1 over C2 plus 1 over C3. And what this tells us is that capacitors in series end up adding the way resistors in parallel did. So that's another thing that kind of pops out of here. And we may have a reason or a way to use this here today. But for now, that'll work. Okay, I wanted to show you some pictures. Just a couple of pictures here. These are some capacitors that you can buy off Amazon now. And they have a lot of capacitance in them. This one, I don't know. I'd have to read the description of this because it's a little bit confusing. It looks like it's 350 farad capacitors. And I'm not positive just what's going on with that. If it's each one of these is 350 farad capacitors or what. Maybe they're connected in series, and that way the equivalent capacitance would be about 58 now that I think about it. Could be. And if you can, there may be reasons to connect them in series for whatever contraption that thing's designed for. But this is also another one. This one's about the size of a Pepsi can, and it's a 500 farad capacitor. Can only take 2.7 volts on it, so not an enormous amount, but still, when we discover soon about energy stored in capacitors, this could have a lot of energy stored in it, possibly. So that may be, or a fair amount anyway. Okay, one other idea I wanted to consider, if I just toss away that note page. Nope, there it is how much energy it takes to store a capacitor, to charge up a capacitor. And we're going to imagine that we already have some sort of a potential difference across this capacitor. And we would have done that by putting some charge onto it. But let's suppose that we've got this thing in a circuit, and over here we've got a battery, which is going to be charging this thing up. And we want to move some amount of charge from the bottom of this, some amount of positive charge from the bottom of this, and take it up top. And how much work would that take? Well, the amount of work done to move charge, a little chunk of charge across a potential difference, is just going to be V dq. Remember, a volt, which is what we measure a potential difference in, we can call it delta V if we want, is a joule per coulomb. And so if we multiply that by some little chunk of charge, we actually get energy, and that's how much work it would take to move that charge across here. And that's the same as if you just took it straight across here, or if you take it all the way around and through the battery does work on that charge in taking it from here and moving it over here. So that's something that we could have. But then let's consider this in terms of capacitance. Capacitance is equal to Q over V, some amount of Q over delta V. And so we could replace the delta V in that thing with Q over C. So now we can think of the little bit of work it'll take is going to equal Q dq over the capacitance. Well, what if we want to charge this thing up from 0 to some final charge? We would integrate both sides of this thing from 0 to W for the amount of work, and from no charge to some capital Q for this thing. And let's see what happens. Well, the left side just integrates to W. That's the total amount of work we have to do. On the right side, I'll have 1 over C times the integral from 0 to capital Q of Q dQ. And I think you know that'll end up being 1/2 Q squared evaluated at 0 and capital Q. It'll end up being 1/2 of the amount of charge stored on the capacitor divided by the capacitance of it. So that would be the work that it takes to charge that capacitor up to something like that. Now I can write this a few different ways. For one thing, the um, let's see. Oh, well, one is the capacitance is equal to the charge on it divided by that final potential difference, whatever it happens to be. And so I could replace Q with C times V, and I could write this amount of work. And by the way, I can stop calling it work and I can start calling it the energy stored in the capacitor. I could write it as 1/2 times 1 over C times Q is C squared V squared, which ends up looking kind of like our spring expression. It's 1/2 CV squared. You remember the 1/2 KX squared for the energy stored in a spring? That's another way that we can write this. You can also write it 1/2 QV if you want to. Bunch of different combinations on there, but that would be the energy stored in the capacitor. So where is the energy stored? How? Turns out it's stored in the electric field. That's kind of amazing. In the electric field. An electric field, just by existing, has energy stored in it. Turns out a magnetic field does too. Well, let's go back to our idea for a parallel plate capacitor. The capacitance of a parallel plate capacitor ends up being epsilon naught A divided by D. So there's a little volume of space in there that it'll have a volume of space that's A times D. And within that little volume of space is where the energy is stored. We could figure out the energy density in that electric field. It will be U is going to equal, let's see, we'll have 1/2 CV squared divided by A times D. Well, let's remember the capacitance is epsilon naught A over D. So let's take 1/2 epsilon naught A divided by D. That's the capacitance. And then V squared over A times D. Oh, let's see, what else can we do here? The delta V is actually equal to E times D or something like this, or just the V potential difference across that. So I can make all kinds of substitutions here. For one thing, the areas divide out. That's kind of nice. And so far, I would have 1/2 epsilon naught V squared over little d squared, but then V is equal to E times D, and we end up with this 1/2 epsilon naught E squared for the energy density in an electric field. And this, we did it just for a parallel plate capacitor, but it turns out it's true for any electric field, no matter where it happens to be. So, okay, maybe we can do some things with that and see where we get. Okay, we have two capacitors, 2 microfarads and 4 microfarads connected in parallel across a 300-volt potential difference. Calculate the total energy stored in the capacitors. I just threw away my piece of paper that had the energy stored in a capacitor, but now remember when we have capacitors in parallel that they just add like resistors in series. And so I'll have, this is 300 volts for our potential difference. There's our one of our capacitors, and here's another one. They'll have the same potential difference across each of them because the electric potential is the same on the top half, and it's the same on the bottom half, and it's a 300-volt potential difference everywhere. So we can have this be the 2.0 microfarad, and here's the 4.0 microfarad. And the total energy stored in here, E total, will equal 1/2 CV squared in each case. So I can say 1/2 C1V squared plus 1/2 C2V squared. And actually, I can just call that 1/2 C1 plus C2 V squared. That's 300 volts. Let's see how the units come out of here. 1/2 of this will be 6.0 times 10 to the minus 6. It's farads, but remember capacitance is charge over voltage. That would be coulombs per volt. That C stands for coulombs. So that many coulombs per volt, and then we're multiplying it by 300 volts squared, which ends up being, let's see, that'll be 9 times 10 to the 4th volts squared, but that makes it coulomb volts. We'll end up with joules here. Okay, and whatever it comes out to, let's see, 9 times 10 to the 4th times 6, that'd be 54 times 10 to the minus 2, I think. 54 times 10 to the minus 2, 27 times 10 to the minus 2, which if we only have 3 significant figures, it'd be 0.003 joules. No, 0.03 joules. But I better check that with a calculator because I was just dancing around in my head there and I'm not positive. Oh, I get 0.27 times 10 to the minus 1. I multiply by 0.5. Yep. Okay. 0.27 joules. And you should work a little, or 0.3 joules. Work a little bit to convince yourself that the units come out. Remember, a volt is a joule per coulomb. Actually, we'll have volts squared, but that divides with that volt to give me Coulomb volts, which just gives me coulombs. Now, for the capacitors in that problem, calculate the energy stored if they're connected in series. So, connected in series, we'd have the 300 volts here, potential difference. And here's C2, here's C1. But remember, 1 over C equivalent. This one seems like it's not too lively either. Is equal to 1 over C1 plus 1 over C2, which is, I get a common denominator of C1, C2. It'll be C2 plus C1 divided by C1, C2. I've got a good one somewhere. Okay. Anyway, C equivalent, there, that's better, is going to be 2.0 microfarads times 4.0 microfarads divided by 6.0. So unit-wise, we end up with microfarads, and that looks like 8 divided by 6, which is 4/3 of a microfarad, or 1.33 microfarads. So that's what we get. And in this case, I could replace those two capacitors with one that has that value, and the energy stored in that case would equal 1/2 times C equivalent times V squared, 1/2 CV squared, and V is still 300 volts. So 1/2 times 4/3 of a, whoops, times 10 to the minus 6, almost forgot that. And again, a farad is a joule per coulomb. No, it's a, let's try that again. C equals Q over V. Farads, coulomb per volt. I don't know what I was thinking. Anyway, times that 3 times 10 squared volts squared. And I will end up with joules again. I feel like doing that in my head. That'd be 9 times 10 to the 4th. 9 over 3 is 3 times 4 is 12, 6. I think it's 0.06 joules, but I better check it again. Yeah, about 0.06 joules. All the way down there. Okay, so less than 1/4 of what we had before. And when you have things in series like capacitors, that equivalent capacitance always ends up being smaller than the smallest of them. Kind of like when you have resistors in parallel, the equivalent resistance ends up being less than the smallest of the resistors that you have. So that's a little bit about those things in series. Here's one. How much energy is stored in 1 cubic meter of air due to the fair weather electric field of 150 volts per meter? So that's the electric field strength, and we just imagine that we have cubic meter of air there. Now, the electric field within that is 150 volts per meter. The electric energy, or the energy density in an electric field, U, is 1/2 epsilon naught, whoops, it's just plain E squared. So we just have to plug into that and figure it out. That's the energy density. The energy total or stored, U, will equal, we've got so many of the same letters floating around here. It'll equal the energy density. I think it's a U, but I'm not positive. Anyway, times the volume. This is energy per unit volume. If we multiply it times our volume, we'll have the actual energy. So I'll have 1/2 epsilon naught is a tiny number, 8.85 times 10 to the minus 12th coulombs squared per Newton meter squared. Times E, which is 150 volts per meter. And that has to be squared. And then times 1 meter cubed. Okay. Unit-wise, what are we going to end up with here? We'll have volts squared. Coulomb squared, volts squared. On the bottom, I'll have Newton meters to the 4th. And then I've got a meter cubed up here. Okay, well, this meter cubed hill will divide with those, and I'll end up with a Newton meter on the bottom, which is a joule. But what about the coulombs times, volt is a joule per coulomb, so this is joules squared per coulomb squared. That divides those. I'll have joules squared on top, and I'll have a joule on the bottom, which leaves me joules, energy-wise. Okay, that's good. So the energy stored in this cubic meter of air is not going to be much, but let's go ahead and multiply out the numbers. It's 50 squared times 1. Anyway, this would be, we've only got 2 significant figures. We'll just imagine that it's exactly a cubic meter of air. And I would get about 1.0 times actually, no, I'm trying to figure out the best way to write this. 1.0 times 10 to the minus 7th joules, I think. Or 0 times 10 to the minus 8th. Yeah, roughly. Anyway, to 2 sig figs, that's about what it would be. Or 1.0 times 10 to the minus 9th joules, which would be, or no, 10 point, yeah, just leave it that way. Good enough. So not much, not a lot of energy in a cubic meter of air, but there are a lot of cubic meters of air over the surface of the Earth, so maybe it comes out impressive. More energy here. Let's see, we have a parallel plate capacitor in vacuum, has 8.38 joules of energy stored in it. By the way, in the vacuum of space, there are still electric fields. And so there is energy in the vacuum of space. But this has 8.38 joules of energy stored in it. The separation between the plates is 2.30 millimeters. If it is decreased to 1.15 millimeters, what is the energy stored if A, the capacitor is disconnected from the potential source, and by that we mean the battery, so the charge on the plates remains constant, or if it remains connected to the potential source, so the potential difference between the plates remains constant. So maybe we better divide this page in half and try to solve this separately. Okay, so for starters, we'll just imagine that we have this parallel plate capacitor that looks like that, and it's got an energy on it that's 1/2 CV squared here, and that energy happens to be 8.38 joules of energy. We know the separation between the two plates. We've got some amount of Q down here and an amount minus Q down there. So that's the energy we've got. And in this case, it is 8.38 joules. Oh man, I'm thinking of a lot of different ways. That's not 18.38, it's 8.38. Thinking of a lot of different ways that I could approach this thing. The capacitance of this capacitor, whatever it happens to be, is going to equal the amount of charge that's on it divided by the potential difference. And I'm not doing anything to the charge, that'll stay fixed, but I am going to be changing the capacitance of this thing. So let's think. The potential difference that's across here, I'm going to write it as delta V, just because delta V is going to be Q divided by C. Delta V initial will equal Q over C initial. Delta V final will equal Q over C final, but if you decrease the separation between the plates, the capacitance changes. C is epsilon naught A over B. You're cutting the decreasing the distance to 1/2 its initial value, which will double the capacitance because the distance between the plates shows up on the bottom of the denominator. And this will be Q over 2C initial. And that means delta V final is going to be 1/2 of delta V initial. So there's something that we need to consider. So what will U final be? U final is going to equal 1/2 C final delta V final squared, but C final is 1/2 C initial, or no, it's twice C initial, excuse me. So U final will equal 1/2 times twice C initial, but delta V final is 1/2 delta V initial. So I'll have 1/2 delta V initial that I'm squaring. And if I factor out all the stuff that I've got in here, let's see, that'll give me a 1/4. This will just give me a 1. I'll have 1/4 out front times C initial delta V initial squared. And somewhere up here, this would have been C initial delta V initial squared. Instead of having 1/2 C initial delta V initial squared, which is 8.38 joules, I'd only have 1/4 C initial delta V initial squared, which is 1/2 of 1/2 C initial delta V initial squared. This is a complicated problem. And this is just part A. Anyway, I'd have half the energy I started with, which looks like 4.19 joules. 4.19 joules. So yeah, well, that's the energy stored here. Now, in that case, if you had two handles on these things and you somehow decrease the distance between them, if you think about it, the top charge is going to have positive charge. Top plate has positive charge on it. The bottom plate has negative charge on it. And you'd have to be exerting forces like that to keep them from just slapping together. So you'd have to be doing negative work on those two plates as you let them get close together. And that's how the energy between them ends up decreasing. Okay, now we're going to do it different here. We're going to leave them connected to the battery here. So we'll have a battery that's sitting here with a delta V initial on it. And then you've got this capacitor over here. And now you're going to do the same thing again, except now the potential difference between the two is going to end up staying the same. Okay, well, if the potential difference stays the same, that means the final energy that we have in here is going to be 1/2 C final times not delta V final, but delta V initial squared. But C final is twice the value of C initial, right? And so what I'll end up with is my final energy in this case will be 1/2 times 2 C initial times delta V initial squared. I'm going to take this 2 and stick it in front and multiply it by 1/2 C initial delta V initial squared. Well, this much is the initial energy we had stored in here. It was the 8.38 joules. and we're multiplying it by 2. So you'd end up with 2 times that, which is 16.76 joules. So in the one case, we ended up with half the energy we started off with. In this case, we ended up with twice as much energy as we started with. So kind of a crazy problem. Now, how would that work out for the forces that you'd have to exert? You'd have to be, oh, I know what's going to be happening is you put these things close together, the battery has to do work to bring more charge around on this thing. So, I think I've got a few more problems on this topic, which I don't have time to get through all of today, but we could stop here for now. We were looking at energy in capacitors, and it's stored in the electric field between the capacitor plates. So it's kind of an interesting thing that's going on here. Okay, any questions on those? I know those were kind of bizarre problems. You might just try them out on your own. Print off the sheet, and even after you've seen them one time, it may not occur to you how to do them. And I know there are other ways to solve these things. As I was doing this, I was thinking you could calculate well, except we didn't know what the capacitance was, so we don't know what the delta V is, but we could have somehow figured out, nope, we don't know the area either. So I was thinking you could somehow figure out the volume here and the electric field strength in it and stuff like that. I guess we could. Knowing the energy and knowing the separation, we could figure out what the area between of them had to be. And then from that, the electric field. But that's just another way of doing it. All
So
right.
I'm in the center with the people who are doing the lab currently, and they're struggling to set up the circuit board. So how would you set it up for in the red box?
Oh, can you say that again? Um,
Um, I'm currently in the STEM center with the people who are struggling to set up the red box for the lab that was last week.
okay.
Who weren't able to